So our next speaker is Professor Tibor Szabó from Freie Universität Berlin, and he's going to speak about reconstructing random graphs in R. It's a pleasure to have you here. Yeah, please.
Yeah, thank you very much for the introduction and the invitation to speak. It's a wonderful event, really. I really enjoy my time here. So, yeah, I was actually thinking twice during the talk in the morning that when I put my mobile under my seat, that you will leave this here. You will leave this here. And I am usually right. So okay, I speak about reconstructing point sets in R, which is a joint work with Richard Montgomery from Warwick, Raiko Nenadov from Auckland, Julien Portier from Cambridge. And let's see what it is about. So our setup is that we have a set of finitely many points in d-dimensional Euclidean space, and we know the distance between some pairs of them. So this is the information we have. So what you can imagine is, and this is a probably non-realistic application, that you have a flock of birds and you would be really interested in knowing how they are flying as a flock, right? So it's a mystery, how can they navigate so fast, so close to each other. You put some nano device on each of these birds, but you can't measure the distance between any pair of them because that would be, I don't know, too many frequencies or too heavy devices. So you decide that you measure only few of the distances between some of the pairs, yet you want to have some information about this. So what are the questions you would like to ask in this situation? The first question is, okay, I know some pairs of distances, points, the distances for some pairs of points. Can I recover all distances between any pair of points? And hence, can I reconstruct the whole shape of the flock up to isometry? The maybe more important question is that not only in this particular position I want to know the shape of the flock, but ideally I would like to know this no matter how the points are distributed or the birds are distributed in the air. So I would like to have a graph G. I'm interested in graph G where if I know the distances for the edges, then I can reconstruct all distances between the points. Finally, if this is too much to ask, then I might also be happy if I would be able to reconstruct the distances within a almost all subset of the points. Okay, so these are the basic questions I will be interested in. Okay, are there any questions? I mean, so far I didn't say anything, so maybe. Okay, that's our setup. So immediately we should note that in order to say something meaningful, we have to make some restrictions on the point set. Otherwise, we can't derive any extra information. So namely, look at the following example. You have n minus 2 points on a line and 2 points outside. Now, if you know all the distances between all pairs except the 2 outside points, then you can't distinguish this configuration from that one, because if you reflect on the line, every other pair will be the same. So even if you have a graph which is like the complete graph minus one edge, you might not be able to reconstruct the whole point set. So the classic way to resolve this issue is to assume generic point sets, which means just that coordinates are algebraically independent over Q. It's a somewhat strong condition that there should not happen anything accidental among the coordinates. And this has a huge mathematical theory and literature, and it has a beautiful math theory behind it. So maybe that's the more important reason to choose this definition. So what did I do? And the beautiful truth in this definition that if you're interested in generic point sets, then it's a property of the graph whether you can reconstruct a point set or you can reconstruct every point set. So if you have one point set, generic point set which you can reconstruct, then you can reconstruct every point set. And this property is called globally rigid in D dimension. There should be the D somewhere here. And I'm going to add here the word generically because my reconstruction will not be of this type. Let's make one simple observation about generically globally rigid graphs. They should be D+1 connected. You can imagine that if there is a cut set of size D, then you could make an embedding of one part of this graph left from the cut set and right to the cut set in the dimensional space. But then you can also simply mirror it on this D element subset. It's on a plane, so you would get two non-isometric embeddings of the same thing. So sort of D+1 connectedness should be true. And it was a long-standing open problem until last year whether some kind of connectivity implies that you are generically globally rigid in the dimension, and this question was answered last year by Soma Villani, who proved that D times D+1 connectedness implies this generically globally rigid in the dimension. And this was known to be best possible since '82 by Lovaas and Yemini, who conjectured this is the correct answer. But before this, there wasn't even any constant known depending only on D. Everything depended also on N, the number of vertices. So this is a very big breakthrough here. Okay. So connectedness is an important parameter here. And this is an important property. So people really studied it from they were trying to understand and still trying to understand what this means exactly. And for D equals 1 and 2, there exists efficient characterizations. But for D at least 3, we don't know such. By efficient characterization, I mean that this is also polynomially, it's in P to decide the property. But for D, no such thing is known, and we don't know. Because of this lack of knowledge, researchers did study also the typical behavior of graphs concerning that. And most recently, Lev, Nevo, Peled, and Raz got an as good result as possible. Namely, they proved that typically G is generically globally rigid in RD if and only if G is D+1 connected. So what does it mean? I'm going to tell you later. It is in form of a random graph process. If you know what it is, at the moment when your random graph becomes d plus 1 connected, it immediately will become globally rigid with high probability. Okay. So this as good as it gets, as d plus 1 connectedness is a necessary condition. Now, what we will talk about is reconstructing in R. And this, as far as I know, was initiated by Benjamin and Zalik not long ago. They were maybe motivated by this construction or the lack of obstruction we have in R to assume genericity of the point set. So the construction which I described earlier, that would be in one dimension, it would be n minus 2 points on top of each other. So to avoid that, it would be enough to just assume that our points are distinct. So this is what we will do. We will not assume genericity. We just want to assume that the points are distinct. The birds don't exactly are not exactly on the same spot. Now, what can we say about that concept? So let's see first about the generic version. So this characterization I was talking about in d equals 1 tells us that G reconstructs every generic point set in R if and only if G is 2 connected. This is an exercise you can try to solve. That if there are no extra regularities, then it's going to be unique how you can embed such a graph. And I put here an example of a graph, the C4, which is generically globally rigid, meaning it is if you assume generic coordinates, then it's uniquely reconstructible, but it does not reconstruct every point set. So in this example, if you see this A, B, and C, D, and then you switch them up, then the edges of the cycle have the same length for both embeddings and right. But the edge between B and D here is length 2, and here is length 4, despite what I wrote, but it's not 2. So you have 2 different ways to embed this distances. Yeah? But here, crucially, these distances will not satisfy the genericity condition or the point set. Okay? Is it clear what I'm saying so far? So good? Right. So besides the cycle, so our goal is here, we assume that we want we want to be able to recover any kind of point set. So C4 will not be our graph, will not be. I have to forbid more graphs if I want to reconstruct more subsets. So there is, in fact, a rich family of 2 connected graphs which do not reconstruct some particular non-generic point set. So one series of examples was constructed by Giraud, Illingworth, Michael Powierski, and Scott, who for every connectivity K, they constructed a graph with that connectivity which does not reconstruct some point set. So they also constructed a point set which is not uniquely reconstructible. And if you look at it and you couple this with the result of Villani, then you see that this also implies that GK, this graph with such high connectivity, will reconstruct any generic point set in a dimension which is roughly square root k. So this is a separation of the so in order to reconstruct point sets in extremely high dimension, even if it's generic, I mean, you have to have some, so you have to have some edges there. But these graphs, these examples, do not even reconstruct in one dimension if you allow arbitrary sets. Yeah, that's what this is saying. Okay, so there is a big separation. This is just to convince you that this family is interesting. It has interesting elements and broad graphs. In fact, Garamvölgyi showed that the decision problem is difficult. So it's going to be complete to decide whether a graph reconstructs every point set in R or not. So if you compare this with what we know about the generic is just two connected, right? So this is a very well understood, efficiently checkable family. And if you extend it, the point sets, then immediately it's CoMP complete. So Benjamin Zalik, because of these difficulties, they studied the random graph, right? So anytime when you are not expecting a characterization which is efficient, it becomes particularly interesting to study the typical behavior. So that's what they did. And what they proved that for any point set on n vertices with high probability, so this is for the students that I explained some notations that this means with high probability, so it happens with probability tending to 1 as the parameter n tends to infinity. So with high probability, the random graph GNC log n over n reconstructs P. You already seen this notation many times. So this just means that you have n vertices and you flip a coin, and with probability C log n over n, you draw an edge, and otherwise you don't draw an edge. So it's a pretty sparse random graph, yet they managed to show that any point set, well, what do they show exactly? I have to be careful. So that for any point set, this random graph with high probability will be able to reconstruct this point set. Okay? So let me make two comments about this. The first is that this result is best possible up to the constant factor. Why? Because if you go below log n over n, then your random graph is not even connected with high probability. Obviously, if you have a disconnected graph, it will not reconstruct anything because you could place one part of it here, the other part here, and then you move the other part there, and then it's, yeah, or you just shift it. So you need two connectivity, in fact, and two connectivity, it's known that the threshold, in a very precise sense, first of all, it's 1 times log n over n, but it's known much more precisely. It's exactly this log n plus log n minus any slowly growing function as n tends to infinity divided by n. This will not be two connected with high probability. And if you would put here a plus slowly growing function, then with high probability it is two connected. So it's very precisely known that this is the threshold for two connectivity. But it's up to constant factor best possible. The other comment I would like to make and would like to draw the attention to is that here in this statement, first they are fixing the points at P, and then they are drawing the random graph. So, and if you think about it a little bit, this is very far from what you really want to know when you have birds, that you don't want to fix first where they are standing and then draw a random graph and then assign them the nano devices accordingly. But you would ideally, you want to have an assignment of the edges beforehand, and then for any P you want to know that you can reconstruct. Although we are living in a one-dimensional universe, right? So imagine that this is a one-dimensional flock which you are trying to follow. So what they conjectured that both of these should be fixable, namely that at the moment the random graph becomes too connected, it should also reconstruct every point set immediately in R with high probability. Okay, so both of these should be improved together. Okay, is the statement clear? Okay. So here, maybe just let me introduce some words which I keep using. So G graph, G reconstruct the and also the terminology I'm going to use now. So I will say that the graph G reconstructs the injective function f from the vertex set to Rd if for any injective function G for which you know that the distances along the edges are equal of G and F. You also know that the distances along any pair are equal. Okay? And that means that F and G are isometric. Okay? And I'm going to call in this talk a graph globally rigid in Rd if it reconstructs every injective function from Vg to Rd. So this is not the standard thing. This is what sometimes called injectively globally rigid, but I will not keep telling this to you. Okay, my main point is that we only consider injective restriction and not generic. And just to understand these notions, here is the phrasing of the Benjamin-Itzalik theorem, is that there is a constant such that if f is an injective function from n to r, then with high probability, if you draw a random graph with h probability c log n over n, this will reconstruct that fixed f. So what is the random graph process? The random graph process is this thing which will be able to measure for us what does it mean that at the moment. So we build a random graph with m edges by adding one by one the edges, always uniformly and random among the edges which you have still free, you did not add yet. So you start with the empty graph, G0, and Gi will be generated from Gi minus 1 by taking an edge uniformly at random out of the remaining free edges. Okay? And now there is this random variable, which I'm going to call tau, which will be my interest, which is the smallest m, such that the smallest time when the minimum degree is at least 2. And it is known that it's very exact time when the minimum degree is at least 2, exactly then, with high probability, the connectivity becomes 2. Obviously, degree 2 is a necessary condition for connectivity, but typically it's also sufficient. And in a subsequent paper, Girao, Illingworth, Michael, Powierski, Scott, which I might just refer to the Oxford group, because I think they are all from Oxford, proved 1/2 of this conjecture. Namely, they showed that for a fixed function, a fixed embedding of the vertices, which are injective, with high probability, if we generate g tau, so the random graph with exactly tau edges, so exactly got the last vertex got its second neighbor, then this will reconstruct F. Okay? And yeah, so in our first main result, we show that you do not, that the parameter, the F, the quantifiers can be exchanged, or I don't know what. So F can be taken inside the G tau, namely, with our new notation, we just proved that with high probability G tau is globally rigid. What does it mean? That for every point set, you can reconstruct it. For every function, injective function from the vertex set to R, you can reconstruct it. First, you generate the random graph, and then you take an arbitrary function, injective function, it will be reconstructed. Okay. And I would like to, before going on, I would like to ask whether you have any question, because I would like to now actually show this statement. Yeah.
So just to make sure that I'm keeping up with it. So this theorem in particular solves the conjecture you had shown.
Yeah, it's exactly the conjecture.
Sorry?
It's the conjecture, yes.
Yes.
And the first half, so I mentioned the two things, right? And in the paper of the Oxford group, they improved the Benjamin-Dzalik theorem in the sense that in the Benjamin-Dzalik here, instead of g tau, you had the gn c log n over n. Now this is heating time. So this is as good as it could get. Okay, because below that, there's no two connectivity. Okay? And what we add to this is that the order is now different. Okay? But not only that, our proof is different, and I think our proof is simpler. And I try to present the combinatorial idea. So there is one combinatorial idea here. Yeah. So the bulk of the proof is this lemma. And this is a deterministic lemma, which is very usual when you prove a theorem about random graphs, that you find some properties, deterministic properties, which imply the property you want to derive for the random graph, and then you show separately that these properties hold for the random graph, which is of your interest with high probability. So this is what we do here. So what is this deterministic lemma? So you have a graph G on n vertices which satisfies two properties. The first one is pretty standard, namely for any pair of disjoint sets, U and W, if they're big enough, big enough means n over 15 in this case, 15 is not so important, it's a constant. There is an edge of G between U and W. The second one is a bit more tricky to see. It says that for any U subset of the vertex set, which is not too small, but not everything, you will find a vertex outside which has degree 2 into this set. Okay? So if you leave out one vertex, it will have degree 2 to the set. What does it mean? It has that essentially, if U is almost everything, then you have one vertex outside. If your minimum degree is 2, you have this property. But it says a bit more. So if there are two vertices outside, it should not be the case that they are connected and each of them just has one edge into the. So 2 degree 2 vertex should not be connected, and so on. So again, this is also true. So these are known properties of the random graph in the G tau. So one just checks that these are true for that. And if you have these two deterministic properties, then G is globally rigid. Okay? Is the statement clear? So here is the lemma, proof of the lemma. We try to show that G is globally rigid. So what we will take is we will take two injective functions where the distances of the images on the edges agree with each other. And then we must show that then the distances between any pairs agree with each other. Okay? And the first idea is to define the left half and the right half for each function. Let me just first say what they are, and then I try to argue why. So the left half of a function f are those indices which are in this line the left half, right? So this has a formal definition, but it essentially says that 7, 6, 1, 13, 9, and 2 are the left half, right? So it's the first half of the thing. And then the right half of the function is just which is on the right side. So which numbers go to the right side, which to the left side. Why do we define this thing? Because when you embedding into one dimension is pretty simple. You have two choices. If you know the distance, you either go to the right or you go to the left. So our goal will be to find some set on the left side and some on the right side, that there are edges in between. Then I will know that I have to go to the right. And I know from here I have to go to the left. So, all right, let's define this. And now, let's look at the two left sides, right? So the G has a left side, the F has a left side, and without loss of generality, you can assume that they intersect in a large chunk, at least 10 over 5. Okay, why is that? If they wouldn't, right, then you could just pass to minus G. Minus G is an isometric copy of G, so if you show the statement for that, it's also good. And the left side and the right side switches. So if you had a small intersection with the left side of F, then now you will have a large intersection with the left side of F. It's going to be at least a quarter, or to avoid the rounding down, n over 5. Okay? And if the left sides have a big intersection, then since the right side are the complement, they also have a big intersection. And that's good, because I want these two pieces I want to have a big piece which is on the left for both functions and on the right on both functions, because I know then which way to go. So yeah, so we name it with L and R, and my claim is that there is a component inside this left intersection and right intersection of the two functions, which is big, in this case n over 15, such that this is a component of the bipartite subgraph, which is induced by G between these parts. So L and R are two subsets, and delete every edge, just leave the ones in between. Now this might have some components, I don't know what. Yeah, so here you can see the components of this bipartite graph. Okay, so there are k of them. Okay, and I'm looking for a big one. I want a big component which is at least n over 15 big. So you can, and then you can just build it. So I'm going to keep adding up the components on the left side. I keep adding it up until you reach n over 15, or on the right-hand side, you keep adding them up until you reach n over 15. You stop when you reached it, So you stopped at this point, and then maybe the left reached it first, and yeah, by definition, it's going to be less than 2n over 15 because we assumed that, that every component has size at most n over 15. So that means it's not more than 2n over 15, but that means that the right is even less. So the left, whatever left on the right side, is at least n over 15. So here we have these two sets. The left side is between n over 15 and 2n over 15. And here you have this right side, which is at least n over 15. But these are two subsets which are big, so our first property will say that there is an edge between them. But that can't be because they are on different sides and they are in different components. So it's a contradiction. So I do have a big component whose size is at least n over 15. Okay, so we showed this claim. I do have this component which has size at least n over 15. Okay. So, yeah, let's take now this largest component and let's take a vertex in it on the left side. Okay, and as my first step, I'm going to shift G such that in this vertex, G prime, the shifted G, agrees with F. I can shift G, this is isometric. And shifting does not affect the sides, right, because nothing happened with the left sides, I'm just moving them. But now I have at least one vertex inside this set U, which represents the vertices where the G prime and the F agree. So G prime and F agree in at least one vertex of U, which is inside the component of our interest and on the left side. Now, you can now easily show that U must be, well, not, yeah, so not easily show, but you can easily show two things. First of all, the whole component should be inside U, right? So you can just think it over. And here, it comes that you know where you are, right? So if you have, for example, some neighbors of this vertex y1 on the left side, it has some neighbors on the right side in this component, then those vertices should also be agreeing. Why? Because I know that this is on the left side for both functions, so it means that for each of the neighbors, I must go to the right and not to the left. So they will also agree in the value in the neighbors. And if they agree in the neighbors, you can take the neighbors' neighbors because they are all in the right side and the neighbors are on the left side. So you have to go left. And then the image is unique. So what I'm saying here is that in this whole component, because just one vertex was in it, every vertex has fix. Yeah.
Are you using information of which is the subset of left and right vertices, not just a graph? You don't have. You don't know.
The L, this, I can use the information because I took a, my root, the y1, is on the left side in both functions. So it is on the left side of both for the F and for the G prime. Or you don't believe this?
I think I'm just confused about what you're allowed to use. So you're using information about point sets. Whether you're allowed to use that. You're using the distances of your graph, and you're looking at the distances between these particular guys.
On the edges, we know the distances.
Yeah, on the edge, you know the distance.
On the edges, we know the distances. So we placed y1 to the same spot for F and G prime.
And then you see the neighbors.
And then I have the neighbors on the right-hand side.
Yeah,
In this component. This is a component in a bipartite graph, right? So
you only know that's a bipartite graph because you know.
I chose it. I chose here this component to be a component of the bipartite subgraph. All right? So if I find in this, suppose this is your component, and then here is the y1. All its neighbors are on the right side.
Because you know they're on the right side.
Well, they are the left was the intersection of the left of the two left sides, and the right was the intersection of the two right sides. So it means that for
Sorry, the point sets are fixed and you know them, and you're just trying to show that they have to be the same up to some translation.
Fixed F and G.
at the moment, all I know is y1 is mapped to the same thing for f and g prime. And because along the edges I know the distance,
So I think the thing I was being stupid about,
no, yeah.
maybe some other people were being involved.
I'm sure that everybody else understands except you. But please.
The thing that I was misunderstanding was,
Yeah.
that you are given 2 point sets, you're allowed to use them, and all you're supposed to do is find some way to translate and reflect until they're the same.
Yeah.
Is that what
Yeah.
you've done? You've made
Right.
reflect-
I already might have made a flip. I already made a translation. And now I want to show that I'm done. They are the same. And first I'm showing that the component is at the right place. And this is because I know that I must go for both functions to the right. It's never to the other side. Yeah, okay. Thank you for the question. No, it's very good that you are a good host. And once you know that the component is there, then you can go and you can use the second property, right, that we have, the P2 property, because now I have a big enough subset because the component is big, n over 15. So I just take a vertex outside whose degree is 2 to my u. And if I have this thing fixed and I have a degree to vertex, you can check the cases. It's uniquely determined, yeah? And then you one by one, because the degree is always 2 to your set, one by one, you can do every vertex, all right? So this is our second property, and that's it. So we showed that, I mean, all this is just writing or looking at there are 3 cases where it is, but it's just formal, yeah? Okay, good. So maybe I ask again, are there any questions about this proof?
I only had a question, I think, that came after Rob's question.
Yeah.
How did you make them induced? Why don't you have edges in between your left side and in between?
I might have edges. I not use them. I don't use them.
Just don't,
For me, it's important that I'm going to look at the components which are induced by the bipartite graph between them.
So yeah, those edges
Yeah.
you are allowed
Yeah.
to ignore.
Yeah, that's just stronger, yeah. So it's a nice, neat proof of this theorem, I think. So in the remaining few minutes, maybe, I don't know, 12 or something like that, I would like to present some more theorems we have proved, either similarly or, and some phenomena and some open questions. Okay, so at the beginning I also alluded to the question, maybe we are happy to just reconstruct not everything but just almost everything. So if we look at the random graph, which should be our thing, which we compare it with, then it is known already by Erdős and Rényi that if the probability is just above linear, or 1 over n, then with high probability you contain a 2 connected subgraph on almost every vertex. Yeah? I'm saying 2 connected because this is to which I should measure myself. This is generic global rigidity, right? Which is an easier thing to do than the injective global rigidity. So I must compare myself always to this. And here, the Oxford group was proving in their setup where they first fix the function, they were proving that for similar probability, so this is much sparser than the log n over n. This is almost 1 over n. With high probability, there will be a subset inside the random graph such that on this almost every subset, this fixed function f can be reconstructed. Okay, and this we can also improve, namely, we show that for every epsilon there is a c, such that if you sample from g and c over n, there will be a v prime with high probability whose size is almost everything except epsilon, such that the induced subgraph is globally rigid. Okay, again, here this is the function is taken after the random graph is generated. So the proof of this is also using our deterministic lemma. So I will not show this now. Another aspect here. So in random graph theory, it is a very, very important question when the phase transition happens, right? So when will the random graph start to have a connected component whose size is linear in n? Okay, for our problem, we are interested more the two connected component, and this, as it turns out, happens, well, for us roughly the same time. I'm sure there are differences, big differences in the epsilon, but the point is that if you go epsilon 1 plus epsilon over n, then with high probability the Gn 1 plus epsilon over n will contain a two connected subgraph on some constant depending on epsilon times n vertices. Yeah. Now, what can we say about our graph property? So, Girao, so the Oxford group proved again by fixing a function, which is injective function, so that if your p is 42 over n, so somewhat larger than this, then you have the the property that the random graph has a linear size vertex set where you reconstruct this function restrict to that. So we strengthen this also two ways. So namely, we again, we don't strengthen this. It's different. So they conjecture that this thing could be the 42 over n could be brought down to 1 plus epsilon over n, but they did not conjecture, as you will see very cleverly, they did not conjecture that you can change the order. Because what we show is that, in fact, that's not true. So what is true is that in the random graph, Gn 1.1 over n, for any v prime whose size is logarithmic, and this should be the other way. So yeah, it's good. So whose size is at least logarithmic, the induced subgraph is not globally rigid. Okay, so I think it's very good because so far all I said to you in the previous theorems that for random graphs, the generic rigidity in R and the injective rigidity in R is behaving the same way. This is showing that there is a difference. Because if you are interested in reconstructing, say, you are reconstructed a linear sized part of your graph, then you will not be, for generic point set, you can do it just at 1 plus epsilon over n, where epsilon could be arbitrarily small. So the phase transition happens for two connectedness at 1 over n. But here, this statement says that if you are interested in the injective point sets, then the phase transition is delayed at least to 1.1 over n. So there is a larger constant over n where you will be able to reconstruct a linear sized chunk, because otherwise you will just be able to reconstruct logarithmic chunks. Yeah, so here again there is a lemma. Here the combinatorial lemma is easier, and there is this other lemma which one can show a little bit similarly as you show that for the normal connected component question, you know that when the constant is less than 1 over n, yeah, then every component size is, every vertex is in a component of size logarithmic. Now here, what we are showing that with probability 1.1 over n, for every v, we could build a set whose size is logarithmic, but where the matching, where between this set and its complement, there is only a matching. And then our combinatorial lemma, which I did not say here, is saying that if you have a graph which has a partition where between these two partition classes you just have a matching, then this is not globally rigid, because you can just embed one part and then you embed the other to the right and then shift it back to the left, and this will be two embeddings. So if there is just a matching in between the two of them, then it's not globally rigid. And because for every v you are able to build such a set, no matter which subsets you are given, whose size is just a bit larger logarithmic than this 6,000, then you will be able to find this partition, which will show that on the v prime you will be not injectively globally rigid. Okay, good. So I want to talk a little bit about open problems. Are there any questions? I think we have maybe a time if you have a question about this statement. Yeah.
I didn't understand what you do with the matching. What's the instruction?
So here it is. So it's the combinatorial part of the statement. It is, you just, so you have A and B and you have a matching in between, or not more than a matching. Then you define two functions, f and g. The f will be just you embed A into the 0, 1 interval injectively, arbitrary. And then you take any neighbor in B, which has a neighbor in A, and you just shift it by 10. That's where you embed it. So these are the B neighbors of A. Okay? Everybody has just one neighbor at most, so there is no contradiction. You just shift it by 10. And for the remainder of B, you put them between 10 and 11, but you avoid the image of A plus 10. Okay? You will not take any of those points.
You assume there's no edges inside A?
There might be edges. I don't care. But I don't care because for the construction of G, I'm just going to take, for A is going to be the same, and for the B, I shift it by 20 back. And this way, exactly the edges will preserve the 10, but everything else will be different. The non-edges will all have different length. So it's a simple lemma, but it does the job if you prove this statement. And as I said, the proof of this is just similar, a bit more complicated when you prove that if you have this Galton-Watson process that if the number of children is less than 1, then you, yeah.
Should we work up to 2 over n?
Two,
If thinking of the Galton-Watson tree, it seems like you should work up to 2. Was that wrong?
no, it's not. It's what you do is that instead of in the original you take a root and then you take you put it into the fixed set and you explore the neighbors, and then you go to the neighbor, one neighbor, you explore the neighbors, you put it here. Now instead of this, you will not put every neighbor immediately there, but if there is just one edge going into there will be a separate container where you put those which have just one edge, and this way the whole thing will slow down so that the average number of additions will be less than 1. So yeah. Okay, so some open problems. Do I have a bit? I started late. I need 3 minutes, really 3. I'm not cheating. So the first is a nice question, I think, about the random deregular graph. So what do we know? What we can show is that there exists some constant d0 such that the random deregular graph is globally rigid. This is just a consequence of the 2 properties which I mentioned, and if you use standard truth about random regular graph like the expander mixing lemma and the eigenvalues of them. Yes? There will be some constant which is, we didn't really try to optimize it because I don't think it's going to get close to the truth. On the other hand, GM3 is not globally rigid. So, and here you can show that almost surely the simple combinatorial criterion I said will hold. In fact, I was also pointed out that if the number of vertices is, so our proof, if you massage our proof, you can even show that every large enough 3 regular graph is not globally rigid. So, but maybe this is a brave conjecture that JN4 is globally rigid already. But if not GM4, then GM5. Okay. For the phase transition, I don't know how realistic is it, but it would be interesting to try to get a better idea about the constant over n when it happens, right? How much you delay it by requiring injective point sets. And well, finally, also there is higher dimension, right? So you can really think of the 3-dimensional birds flying. And of course, here there is no hope for non-trivial injective global rigidity. So you can't do the whole point set. But you can still do maybe almost everything. And the question would be, is that what's the probability which you require so that you can reconstruct in 2, 3 D dimension almost everything? And now I'm talking about injective point sets, so not generic, but injective. And here, I mean, the best would be, of course, something like C over n, but we don't know anything. So I think the bounds which there are some papers about this problem, and what people know is something polynomial in n. So not polynomial reversed, then the best possible. Okay, so let me stop here.